Welcome everyone to this comprehensive session on Introduction to Data Science and Analytics. Whether you're a student stepping into the world of data, a professional looking to pivot your career, or someone simply curious about how companies make data-driven decisions, this presentation is crafted to provide a solid foundational understanding of data science and analytics. Over the next few slides, we'll explore what data science and data analytics truly mean, how they differ, and how they come together to power decisions in industries ranging from healthcare to finance to retail and beyond. We'll begin by defining the core concepts. What exactly is data science? How is it different from data analytics? Why is everyone from small startups to large multinational corporations investing heavily in these domains? Then, we'll walk through the life cycle of a data science project. A process that begins with understanding a business problem, then collecting and cleaning data, analyzing it, building models, and finally deploying those models for real-world use. This life cycle provides a structured approach to solving problems with data. Next, we'll identify the different roles in a typical data science team. Just like a movie needs actors, directors, editors, and producers, a successful data science project relies on a diverse team: data scientists, data analysts, data engineers, ML engineers, and business analysts, each contributing a unique skill set. We've structured this presentation to be beginner-friendly, yet insightful enough for those with some experience. Each slide will contain either bullet points or an in-depth paragraph explanation, accompanied by practical examples and tools used in the industry. Some slides will provide high-level overviews, while others will dive deeper into processes and techniques. The ultimate goal of this presentation is to demystify the field of data science and analytics. These terms are often used interchangeably, and while they are related, they serve different purposes. By the end of this session, you will not only be able to differentiate between them, but also understand how they work together to generate insights, drive strategy, and create intelligent systems. Whether you are looking to pursue a career in this domain, or are just looking to apply data-driven thinking in your own organization, understanding these fundamentals is a critical first step. So, let's begin our journey into the world of data, where numbers tell stories, and insights lead to impactful decisions. Thank you for joining me today. Let's get started. What is data science? Data science is the field that focuses on extracting meaningful insights from vast volumes of structured and unstructured data. It combines multiple disciplines, including statistics, mathematics, computer science, and domain-specific knowledge, to uncover trends, make predictions, and support decision-making. At its core, data science involves using data in creative and systematic ways to solve real-world problems. The goal of data science is not just about collecting data, but understanding it, analyzing patterns, drawing conclusions, and turning those insights into actionable knowledge. Think of it as a toolkit filled with techniques like machine learning, data mining, and predictive modeling. Data scientists use these tools to discover unknown relationships and provide foresight that drives smarter business strategies. For example, in healthcare, data science helps predict patient readmissions or detect diseases early. In retail, it powers recommendation engines and optimizes inventory. In finance, it detects fraud and assesses credit risk. These applications highlight how critical data has become in today's digital world. A successful data scientist blends technical skills with critical thinking. They ask the right questions, choose the appropriate models, and communicate their findings clearly. As organizations increasingly rely on data to stay competitive, data science has emerged as one of the most sought-after fields globally. Why is data science important? Data science is a powerful driver of innovation, efficiency, and strategic decision-making across nearly every industry. In today's digital age, companies are flooded with data, from customer behavior to operational performance. But without the ability to interpret and act on that data, it's just noise. This is where data science becomes crucial. With data science, organizations can transform raw data into valuable insights. These insights help reduce costs, improve customer experience, identify new market opportunities, and even predict future trends. For example, airlines use data science to optimize flight schedules and pricing. Hospitals use it to monitor patients and prevent complications. Even sports teams use it to enhance player performance and game strategy. Another reason data science is essential is its role in automation and intelligent systems. From self-driving cars to chatbots and recommendation engines, these technologies are all powered by data-driven algorithms developed by data scientists. This not only creates better user experiences, but also leads to the development of smarter products and services. As we move toward a more data-centric world, the demand for professionals who can analyze and interpret data continues to grow. Data science isn't just a trend, it's a fundamental skill set shaping the future of business, science, and technology. Embracing it enables organizations to innovate, remain competitive, and prepare for what lies ahead. What is data analytics? Data analytics is the systematic process of examining datasets to draw conclusions and support decision-making. It focuses on analyzing historical data, identifying patterns, and finding trends that help organizations understand what has happened and why. While data science is broader and often predictive or prescriptive, data analytics tends to be more descriptive and diagnostic in nature. There are four main types of data analytics: descriptive, what happened; diagnostic, why did it happen; predictive, what is likely to happen; and prescriptive, what should we do. These methods allow businesses to go beyond guesswork and make decisions based on evidence and logic. Data analysts use tools like Excel, SQL, Python, R, and visualization software such as Tableau or Power BI to carry out their tasks. They clean and organize raw data, run statistical tests, and present findings in charts or dashboards that are easy for stakeholders to understand. For instance, a marketing team might analyze customer demographics and purchase history to create targeted campaigns. In logistics, analytics can uncover bottlenecks in supply chains. These insights not only help in solving current issues, but also in preventing future problems. In essence, data analytics bridges the gap between raw data and strategic decisions. It empowers organizations with the clarity they need to move forward with confidence. Data science versus data analytics. Although the terms data science and data analytics are often used interchangeably, they serve distinct purposes and operate on different parts of the data value chain. Data science is a broader field focused on building models and algorithms to predict outcomes and automate decisions. It's exploratory, experimental, and often deals with future scenarios. Data analytics, on the other hand, focuses on interpreting existing data to find actionable insights. Think of it like this: data analytics tells you what is happening now, or what happened in the past, whereas data science aims to tell you what could happen in the future, and even recommends actions. While both roles require data wrangling and visualization skills, data scientists typically have a stronger background in machine learning and programming. From a business standpoint, data analytics is great for performance reporting, dashboarding, and identifying patterns in operational data. Data science, in contrast, is used for advanced use cases like fraud detection, natural language processing, or recommendation engines. Both disciplines are essential. In fact, many projects require collaboration between data scientists and data analysts. Their combined efforts help businesses not only understand their current position, but also plan intelligently for the future. Understanding the distinction helps professionals choose the right tools, techniques, and roles suited to their goals and business needs. Real-world applications. Data science has revolutionized how industries operate by transforming raw data into actionable insights. In healthcare, predictive models help identify patients at risk of diseases like diabetes or heart conditions, enabling early intervention and personalized treatment. In finance, data science is instrumental in fraud detection systems that analyze transaction patterns in real time to flag anomalies. Banks also use machine learning to assess credit risk and offer tailored financial products. In retail, companies leverage customer behavior data to optimize inventory, recommend products, and enhance user experience. Transport and logistics firms use data-driven insights for route optimization, reducing fuel costs, and improving delivery efficiency. Even in agriculture, data science supports precision farming, analyzing soil, weather, and crop data to increase yield. These real-world applications demonstrate the versatility of data science across sectors. With the explosion of data from digital platforms, sensors, and IoT devices, industries now rely on data scientists to derive value, streamline operations, and innovate continuously. As you delve deeper into data science, understanding its impact on various domains will help you appreciate the importance of context when developing models and solutions. Life cycle of a data science project. Understanding the life cycle of a data science project is essential to navigating the complexities of real-world problems. The process typically starts with problem understanding, clearly defining the objective in business terms. This is followed by data collection, where relevant data is gathered from databases, APIs, web scraping, or sensors. The next stage is data cleaning and preparation, which includes handling missing values, removing outliers, and transforming the data into a usable format. Once the data is ready, exploratory data analysis, EDA, is performed to understand patterns, trends, and relationships within the dataset. This phase helps guide the model building process. Modeling involves selecting the right machine learning algorithms, training and validating them, and tuning hyperparameters to improve performance. Once a model is finalized, it moves to the deployment stage, where it's integrated into a production environment, often via APIs or web services. Post-deployment, continuous monitoring is essential to track model performance and retrain it if it begins to drift. This iterative life cycle ensures that data science solutions remain aligned with dynamic business needs and continue delivering value over time. Each step is interconnected, and skipping one can compromise the outcome. Problem understanding. Every successful data science project starts with a deep understanding of the problem. This step focuses on identifying the core business objective and translating it into a well-defined data science question. For example, if a hospital wants to reduce patient readmission rates, the problem needs to be framed in measurable terms. Can we predict which patients are at high risk of readmission within 30 days of discharge? Understanding the problem involves interacting with stakeholders, reviewing existing workflows, and analyzing historical performance. Clear problem definition helps in setting the scope and avoiding project drift. It also influences what data is collected, which modeling techniques are selected, and how success is measured. This stage is not about jumping into code or data, but about asking the right questions. What decisions will be influenced by the model? What are the constraints, technical, legal, or ethical? What is the expected outcome? Thorough problem understanding lays the foundation for the rest of the project. It ensures that your efforts align with business goals, and that the model ultimately delivers real value rather than just statistical accuracy. Always begin with clarity before moving on to data. Data collection. Once the problem is clearly defined, the next step is data collection. This is the process of gathering relevant data that will help answer your research or business question. Sources can include internal databases, CRM systems, online APIs, web scraping tools, public datasets, or even sensor and IoT device feeds. The quality and quantity of your data significantly impact model performance. It's important to consider the type of data you are collecting: structured data like tables and spreadsheets, semi-structured data like JSON or XML files, and unstructured data like images, audio, or free text documents. For instance, if you're predicting customer churn, you might collect data on demographics, purchase history, interaction logs, and customer service tickets. A key part of this stage is ensuring the data is legally and ethically sourced, especially when dealing with personal or sensitive information. It's also essential to maintain a record of how and from where each dataset was obtained to support transparency and reproducibility. Data collection may seem straightforward, but often requires collaboration across teams, robust documentation, and automated scripts to ensure efficiency and consistency over time. Data cleaning and preparation. After collecting data, the next crucial step is cleaning and preparation. Raw data is rarely perfect. It often contains missing values, inconsistencies, duplicates, and errors that can negatively affect model performance. This stage involves identifying and addressing these issues. For example, you may fill in missing data using statistical imputation methods, remove irrelevant columns, or correct data entry errors. Standardization is also essential, for instance, ensuring date formats, units of measurement, or categorical labels are consistent across the dataset. Another key activity is data transformation, such as normalizing numerical values or encoding categorical variables into machine-readable formats. Outlier detection and handling is also part of this step, since extreme values can skew model results. A clean and well-prepared dataset ensures that the models built later are both accurate and reliable. In many real-world projects, this step can consume up to 70 to 80% of the entire time, because of its complexity and importance. Automation using Python libraries like Pandas and NumPy can speed up the process, but human judgment is irreplaceable when making contextual decisions. Skipping or rushing this phase often leads to flawed analysis and poor model performance, making it one of the most critical steps in the data science life cycle. Exploratory data analysis, EDA. Exploratory data analysis, EDA, is where the data begins to speak. Once cleaned and prepared, the data is explored through visual and statistical techniques to uncover patterns, trends, and relationships. The main objective of EDA is to gain a deep understanding of the dataset before modeling. You might start with summary statistics like mean, median, standard deviation, and correlation matrices to get a high-level view. Visualization tools such as histograms, box plots, scatter plots, and heat maps can reveal data distributions, outliers, and interactions between variables. For example, in a dataset of patients, EDA can help you discover whether age or previous conditions correlate strongly with readmissions. Tools like Python's Matplotlib and Seaborn or BI tools like Tableau, are widely used in this stage. EDA also helps validate assumptions, checking if the data meets the requirements for the intended model. Any unusual patterns or inconsistencies can be flagged for further investigation. Moreover, EDA can help generate hypotheses and guide feature engineering by identifying which variables might be most influential. This step is about being curious and asking questions, which can lead to surprising insights and better model design. Good EDA can often determine the success or failure of a data science project. Modeling and algorithm selection. Modeling is the heart of a data science project. Once you've explored the data and understood the key variables, it's time to choose and apply the right machine learning algorithms to make predictions or classifications. The choice of model depends on the problem type, classification, regression, clustering, or recommendation. For example, logistic regression or decision trees are often used for binary classification problems like predicting churn. For continuous outcomes, such as predicting sales, linear regression or random forests might be used. Each algorithm has its strengths and assumptions, so it's vital to experiment and evaluate multiple models. The process includes splitting the data into training and testing sets, fitting the model on training data, and validating it using accuracy, precision, recall, or other metrics. Hyperparameter tuning, via techniques like grid search or cross-validation, is often needed to optimize model performance. In addition, feature selection and dimensionality reduction can help improve accuracy and reduce overfitting. It's essential to document all choices, parameters, and results for reproducibility. Modeling is not just about achieving high accuracy, it's about building interpretable, robust models that solve the business problem effectively and reliably. Model deployment and monitoring. After a model is trained and validated, the next step is deployment, making it accessible for real-time or batch predictions. Deployment can be as simple as integrating the model into an Excel spreadsheet, or as complex as hosting it on a cloud-based API used by multiple systems. Common platforms for deployment include AWS SageMaker, Google Cloud, Azure ML, and container-based solutions like Docker and Kubernetes. The goal is to operationalize the model so it provides value to users. But the job doesn't end here. Continuous monitoring is essential to ensure the model performs well over time. Data drift, where the nature of input data changes, can degrade model accuracy. That's why organizations set up automated pipelines to log performance metrics and alert data scientists if retraining is required. Version control for models, rollback options, and proper documentation are also critical in production environments. Monitoring involves not just technical metrics, but also business KPIs, ensuring the model meets real-world needs. Deployment turns your work from an academic exercise into a real solution. It connects data science to decision-making, creating tangible impact. A well-deployed model becomes a living system, adapting and evolving along with the data and business environment. Key roles in a data science team. A successful data science project requires a multidisciplinary team, where each role plays a specific function. The data scientist is at the core, responsible for exploring data, building models, and validating results. They need strong skills in statistics, programming, and machine learning. Data analysts focus on interpreting data and creating visualizations and dashboards. They provide insights that guide business decisions and often bridge the gap between raw data and strategic planning. Data engineers are critical for building and maintaining data pipelines, ensuring data is accessible, clean, and structured. They work with large-scale systems and cloud platforms to manage storage and processing. Machine learning engineers specialize in deploying models into production environments, focusing on scalability, performance, and automation. Business analysts ensure that the technical work aligns with organizational goals. They help frame the problem, gather requirements, and interpret results for stakeholders. Additionally, domain experts bring industry-specific knowledge that enhances model relevance and accuracy. These roles must collaborate closely, using tools like Git, Jira, and Slack to coordinate effectively. Each role complements the others, and communication is key. Understanding the full spectrum of team responsibilities helps aspiring professionals find their niche and contribute meaningfully to data-driven solutions. Thank you for your attention. We've covered the definition and importance of data science and analytics, explored how they differ, walked through the data science project lifecycle, and understood the roles that bring a project to life. I hope this session has deepened your understanding and sparked your curiosity to explore further.